Hello, this is Dr. Brown. In this video, we're going to do the last installment in our modeling unit, and we're going to be talking about exponential functions. And this is on page 182 to 188 in the textbook. Now, to start off with, we're going to have a sort of a little introduction or overview of what we're talking about. We're going to be talking about modeling exponential functions that describe what I call astounding growth, as well as hope for quick decay. That means there are some things we like to go down, like them to go down and decrease quite rapidly, and we call that decay. There are things we want to increase, for instance, our economy, our technology, our income, life expectancy, etc. All kinds of things you would like to see grow. There are things we would like to see a great decrease in. That would be deaths by war and violence, unemployment, disease, and crime rate, as well as other things I'm sure you could think of you would like to see go down. Now, in my experience, I remember the year 2006. This was a year that the population of the United States reached 300 million. And if you go back to the early days of the U.S. back in about 1790, shortly after the revolution, when our population was 4 million, you can see there's been quite an increase in population over that time. And we can describe that as exponential growth. It's not linear growth. If the growth had been linear, it might have gone sort of like this in a straight line. But for us, the population went up very rapidly. Now, I'm going to also give you a little information about some of my experience in technological growth. When I was just a 2-year-old babe in 1947, a company, Bell Laboratories, that does the research and development, or did the research and development for AT&T. These three men invented the transistor. Back in 1947. And here is a model of the transistor. It was a great breakthrough in electronic miniaturization. At one time, to provide amplification in, say, a PA system, you would need what we call tubes. Now they have a little transistor that can do that amplification. When I was in high school, back in 1963, I remember using my first transistor that looked like this. It had 3 wire leads on it, and I used that to design a circuit to guide a robot along a programmed path. And this is the robot in my hand here. You really can't tell that much about it, but it would follow a path that you marked on the floor, or would say a piece of tape around, say, the gym, and it would follow that path automatically. It would be guided along the program path. So that was back in 1963. By 1964, when I was at Georgia Tech, I saw my first chip that had multiple transistors on the chip. And I used this back in 1964 to design digital circuits. And I thought it was just wonderful that there were 6 transistors on the chip. However, go 10 years forward, and Motorola, I'm sorry, not Motorola, but Intel Corporation, who I'm sure you've heard of, came up with a chip with 2,250 transistors on it, used in the first computer that I had when I joined Bell Labs in 1974. I was very excited about joining Bell Laboratories. Actually, I joined in 1971, and I remember the first computer I had in 1974, I believe had an Intel chip on it with about 2,200 transistors. Fast forward to this day and time, in 2019, I have a computer at home that I use to make and edit videos for our class, and it's got 2.1 billion transistors on it, which is a tremendous increase, which is said to be exponential. Now here is a plot of versus year from back in 1970 to 2018 of the number of transistors on various microprocessor chips that have come out over these years. And as you can see, in this day and time, you will see some with like 20 billion transistors. And that is why you have in your cell phone a chip that has billions of transistors on it, and it can do things like GPS, guide you in your car from here to there, talking to a satellite that's up several hundred miles up above you. In fact, it's talking at least to 3 satellites if it's going to guide you in all the various ways it can. Now, let's talk about exponential functions and exponential growth. You already know about exponential growth because when we figured out how much our deposits in a bank might grow to, with time, we came up with this exponential equation where R was a growth rate, N was how many times during the year the bank account was compounded in interest, and then T was the year. Now, if N is 1, in other words, you do it just once per year or once per period, the equation becomes the present value times 1 plus R to the power T. Now, if we change our notation a little bit and let P sub 0 be the starting value, the future value is equal to the starting value times 1 plus R to the T power, where T is in years or in the number of periods that the increase occurs over. Now, if you put in T equal 1 just for 1 year or 1 period after the first year, the amount you have is equal to P0, what you had at the beginning of the year, times 1 plus R for a growth rate of R per period. Now R needs to be in decimal form. Now what this means is that the next period amount is equal to 1 plus R times the last period amount. And you recall that if, say, R were 3%, or big R was 3%, then little r was 0.03. And so the next period amount would equal to 1 plus 0.03 times the last period. And now we go into the formal equations. If you have a quantity that starts at size P0 and grows by capital R%, written as a decimal R, and this happens every time period, then the quantity after n time periods can be determined using either of these relations. The first is the recursive form, where for the nth time period, the amount you have then at the end of that is equal to 1 plus R times the n minus 1 time period. So, for instance, P, the 10th time period, is going to be 1 plus R times P9, what you had in the 9th time period. And in explicit form, P sub n is equal to what you started off with n periods ago times 1 plus R to the nth power. And we call R the growth rate, which can be positive or negative. For instance, if it was growing, R is 0.03. If it were decreasing, R is equal to minus 0.03. And the term 1 plus R is called the growth multiplier, or the common ratio. And this can be more than 1 or less than 1. If it's more than 1, it's growing. If it's less than 1, it's decaying or decreasing. Here's our first example. Suppose that a lake began with 1,000 fish, and 10% of the fish are surviving, have surviving offspring each year. So we want to complete the table using the explicit or recursive form of the equation. Well, we're going to start off with 1,000. In year 1, we'll multiply everything by the growth multiplier, which would be 1.1, or 1 plus R equal 1 plus 0.1 equal 1.1. So then this would be 1,100 fish that you would have in year 1. And then in the next year, you would have 1,100 times 1.1. And if you go ahead and complete this all the way up to year 20, you will have grown to well over 6,000 fish. And if you plot this, plot the points that you just calculated all the way up to 20, and put dots where you calculated, this is what the graph looks like. If you put this in your calculator, we would have P sub n is equal to 1,000 times 1.1 to the nth power. Or we could let n equal t, where t is is years. Then we would get this smooth curve, which was at each year what the population would be. Now, let's learn how to interpret an equation. Suppose you have a friend who's using the equation P sub n equal 4,600 times 1.072 to the nth power to predict the annual tuition at a local college. She says the formula is based on years after 2010. So what does this equation tell us? It tells us that the local college's tuition has constantly increased by 0.072 or 7.2% every year since 2010. Now, the city of Tacoma, Washington's population in 2000 was 200,000, and it's been growing by about 9% each year. We want to write a recursive formula for the population of Tacoma. Now, the growth rate is going to be 9%. In decimal form, R is 0.09. The growth multiplier then would be 1 plus R equal 1.09. And so the recursive formula would be P sub n, the nth period is going to be 1.09 times to the n minus 1 period. Now, if we want to have an explicit formula for the population of Tacoma, it would be the starting value, which would be 200,000 times 1 plus R to the n, which is going to be 1.09 to the nth power. So if the trend continues, what would the population be in 2016? Well, n is going to be 2016 minus 2000. This would be 16 years past the year 2000. So the explicit formula would be 200,000 times 1.09 to the 16th power is equal to 794,061.18, and we would round that off to 794.61. Now here's an example of decay, or basically eating your M&Ms. Suppose you have a bowl of 500 M&M candies, and each day you eat a quarter of the candies you have. Is the number of candies left changing linearly or exponentially? Well, P sub n is going to be 500 times, in this case, 1 minus little r. Little r is 0.25. So the recursive formula would be, or the explicit formula would be 500 times 1 plus r, which is going to be 1 minus 0.25 equal 0.75. So each period, or each day, we have 500 times 0.75 to the nth power. So trying to figure out how much you have after 1 week. 1 week is n equals 7 days. And so in 1 week, you would have 500 times 0.75 to the 7th power, which is 66.74. After 10 days, it's 500 times 0.75 to the 10th power is 28.16. After 2 weeks, that's 14 days, you'd have 8.91. And finally, after 3 weeks, which is 21 days, you would have 1.19. So you're back about down to your last M&M. Now, graphing this, it would look like this. So based on this data, when can you expect all of the M&M candies to be eaten? In approximately 22 days. 21 days, you're down to 1. And you're going to eat that on the 22nd day. And of course, this says you have 0.19 left, but basically you're down to no M&Ms to eat. And the smooth curve would look like this. Now we have one last example. In 1990, the residential energy use in the U.S. Population was responsible for 962 million metric tons of carbon dioxide emissions. By the year 2000, that number had risen to 1182 million metric tons. If the emissions grow exponentially and continue at the same rate, what will the emissions grow to by the year 2050? So we're talking about 60 years past 1990. So similar to the previous examples, will correspond n equals 0 with the year 1990, as that is a year for the first piece of data we have. So we'll make P0 equal 962. In this problem, we're not given the growth rate, but instead are given that P10, piece of 10 is equal to 1182. So we're going to put, when n equal 10 in the explicit equation, P10 equal 1 plus R to the 10th power times P0. So we have that P0 is 962. And we also have the fact that P10 is equal to 1182. So we know that plugging in what P10 is, we get 1182 equal 1 plus R to the 10th power times 962. Now we write down 1182 equal 1 plus R to the 10th power times 962. We now divide both sides by 962, and we get 1182 over 962 equal 1 plus R to the 10th power. So 1 plus R equal the 10th root of 1182 divided by 962. So solving for R, we subtract 1 from each side, and we get R is equal to the 10th root of 1182 over 962 minus 1 equals 0.020808, or 2.08%. So now if we use the formula for 2050, when n equals 60, we get that the population 60 years later is 1 plus R to the 60th power times P sub 0, which is 962. So we get 1.02 0808, which is the 1 plus r to the 60th power, and we get 3,209.93, which we would round off to 3210 to the nearest whole number. And that is the section on exponential functions.